This is SpaceTime Series 20, Episode 31. Coming up on SpaceTime, discovery of a potential new dwarf planet in the outer reaches of our solar system, detection of a record-breaking neutron star pulsar system, and 3 Aussie satellites launched aboard a Cygnus cargo ship bound for the International Space Station. All that and more coming up on SpaceTime.
Welcome to SpaceTime with Stuart Gary.
A distant member of our solar system could be the latest in a growing group of celestial bodies known as dwarf planets. A report in the astrophysical journal Letters claims new measurements of 2014 UZ224, and more informally known as DeeDee, indicates it's roughly 635 kilometres wide. That's about 2/3 the diameter of the dwarf planet Ceres, the largest object in the main asteroid belt between Mars and Jupiter. It's also large enough to have sufficient mass to be self-gravitating, in other words round, and that's one of the criteria necessary for astronomers to consider it a dwarf planet. At about 3 times the current distance of Pluto from the Sun, DeeDee is the second most distant known trans-Neptunian object with a confirmed orbit, surpassed only by the dwarf planet Eris. Trans-Neptunian objects include frozen worlds, comets and icy debris circling the Sun out beyond Neptune in the Kuiper belt and the more distant Oort cloud. Astronomers estimate there are tens of thousands of these icy bodies in the outer solar system out beyond the orbit of Neptune. The study's lead author, David Gerdes from the University of Michigan, says the region out beyond Pluto is surprisingly rich in planetary bodies. While some are quite small, others have sizes to rival Pluto, and some may even be larger. Gerdes says because these objects are so distant and so dim, it's incredibly difficult to even detect them, yet alone study them in any detail. However, by using ALMA, the Atacama Large Millimetre Submillimetre Array Telescope in Chile, astronomers were able to reveal some extraordinary details about this far-flung member of our solar system. Currently, DeeDee is about 92 astronomical units from the Sun. An astronomical unit is the average distance between the Sun and the Earth, roughly 150 million kilometres or 8 light minutes. Light from DeeDee takes about 13 hours to reach Earth. At this tremendous distance, it would take DeeDee more than 1100 years to complete one orbit around the Sun. Gerdes and colleagues originally found DeeDee using the 4-metre Blanco telescope at the Inter-American Observatory in Chile. It was discovered during observations for the Dark Matter Survey, an optical survey of about 12% of the sky that seeks to understand the as-yet mysterious force of dark matter which is causing the expansion of the universe to accelerate. The Dark Matter Survey produces troves of astronomical images, giving scientists the opportunity to also search for distant solar system objects. In fact, the initial search, which includes over 1,500 images, has identified more than 1.1 billion candidate objects. The vast majority of these turned out to be background stars and even more distant galaxies. However, a small fraction were observed to move slowly across the sky over successive observations, and that's a telltale sign of a trans-Neptunian object. One such object was identified on 12 separate occasions. Astronomers informally named it DeeDee, which is short for distant dwarf. The optical data from the Blanco telescope enabled astronomers to measure DeeDee's distance and orbital properties. However, they were unable to determine its size or other physical characteristics. It was possible that DeeDee was a relatively small member of our solar system, yet reflective enough to be detected from Earth. On the other hand, it could be an uncommonly large but dark object, reflecting only a tiny portion of the feeble sunlight reaching it. Both scenarios would produce identical optical data. Because ALMA observes the cold dark universe, it's able to detect the heat in the form of millimetre wavelength light emitted naturally by cold objects in space. The heat signature of a distant solar system object would be directly proportional to its size. The authors calculated that this object would be incredibly cold, only about 30 degrees Kelvin. That's just a little above absolute zero. While the reflected light coming from DeeDee is only as bright as a candle seen halfway the distance to the Moon, ALMA was able to quickly home in on the planetary body's heat signature, measuring its brightness in millimetre wavelength light. This allowed astronomers to determine that it reflects about 13% of the sunlight reaching it. By comparing these ALMA observations with the early optical data, astronomers had the information necessary to calculate the object's size. Objects like DeeDee are cosmic leftovers from the formation of the solar system. So their orbits and physical characteristics can reveal important details about the formation of planets, including Earth. This discovery is also exciting because it shows that it is possible to detect very distant, slowly moving objects in our own solar system. And of course, the same technique could be used to detect the hypothesized planet 9, which, if it exists, resides far beyond DeeDee and Eris. This is Space Time. I'm Stuart Gary. Citizen scientists have helped astronomers discover an unusual record-breaking double neutron star system. The findings, reported in the Astrophysical Journal, will help scientists better understand and test Albert Einstein's theory of general relativity, which explains the interaction of mass with the fabric of space-time. Neutron stars are the stellar corpses of stars far more massive than the Sun, which have been destroyed in core collapse supernova explosions. These powerful cataclysmic blasts, marking the death of some of the universe's biggest stars, are bright enough to outshine entire galaxies. A neutron star is the highly magnetized, extremely dense core remnant of the star that exploded. Neutron stars spin rapidly, emitting powerful beams of energy into space as they rotate. These rapidly rotating beams look like celestial lighthouse beacons pulsing in the night. If Earth just happens to pass through one of these beams, large radio telescopes can detect the neutron star as a pulsating radio source, hence the term pulsar. Because neutron stars are born out of massive stellar explosions, they're thought to often end up blowing away any companion stars or planets in their systems. In fact, of the 2,500 known pulsars, only 255 are in binary systems with another star. And including this latest discovery, only 14 pulsars are in binary systems with another neutron star. This newly discovered double neutron star system, detected 25,000 light-years away, is by far the most massive. Each star is easily more massive than the Sun, but they each contain such condensed matter they're each only 20 kilometres in diameter. Astronomers have calculated that the combined mass of these two dead stars is about 2.88 times that of the Sun. They were discovered in data from the Arecibo Radio Telescope in Puerto Rico with the help of a volunteer distributed computing project called Einstein at Home, which is similar to the SETI at Home project. Einstein at Home aggregates the computing power provided by more than 40,000 volunteers from all around the world on some 50,000 laptops, PCs and smartphones. It's one of the world's largest distributed volunteer computing projects, and its computing power of 1.7 petaflops puts it among the 60 largest supercomputers in the world. One of the study's authors, Bruce Allen from Germany's Max Planck Institute, says as well as being unique cosmic laboratories for undertaking some of the most precise tests of general relativity, double neutron star systems can also play an important role as potential gravitational wave sources for the Laser Interferometer Gravitational Wave Observatory LIGO detectors. That makes these rare double neutron star systems important laboratories for fundamental physics, enabling measurements that are simply impossible to obtain in any Earthbound laboratory. The newly discovered pulsar is known as PSR J1913 plus 1102. The name provides scientists with its exact position in the sky by right ascension and declination. The plus sign indicates the north celestial hemisphere, while the negative sign indicates the south celestial hemisphere. After the initial discovery of the binary system by Einstein at Home in 2012, astronomers observed the system repeatedly using the Arecibo dish in Puerto Rico to precisely measure the orbit of the radio pulsar. They found that PSR J1913 plus 1102 spins once every 27.2 milliseconds. That's 37 times a second. Their observations also showed that this object actually consists of two neutron stars, orbiting each other in a slightly elliptical orbit in a little under 5 hours. Only one of the neutron stars, however, can be seen from Earth as a pulsar. By measuring how the pulsar rotates slightly slower over time, astronomers could also infer its magnetic field to be a few billion times that of Earth. Now, that's relatively weak for a neutron star, and it could indicate an episode of matter accretion from the companion star sometime in the distant past. That accretion episode, however, would also have circularized the orbit. The observed ellipticity of the orbit is testament to the companion star also exploding in a supernova and leaving behind a second neutron star. Amazingly, the kick of the two supernovae didn't disrupt the binary system, but simply made their orbits elliptical. Thus, the record-breaking system shows Einstein's relativity in action. Moreover, the authors were able to measure the effect of Einstein's general theory of relativity in the binary system. You see, like the orbit of Mercury around the Sun, the elliptical orbit of the radio pulsar tends to rotate over time. While the elongation of Mercury's orbit only rotates about 0.0001 degrees per year, J1913 plus 1102's orbit rotates some 47,000 times faster. That's a full 5.6 degrees each year. The magnitude of this effect, known as relativistic periastron advance, depends on the combined mass of the radio pulsar and its companion, thereby allowing a measurement of its quantity. Astronomers expect the neutron star, which is seen as the pulsar from Earth's point of view, to be heavier than the companion star. However, current observations aren't letting them determine the individual masses of the two stars. Still, astronomers are hoping continued observations will allow this measurement to be made. If the pulsar does indeed turn out to be significantly more massive than the companion, then this system will be significantly different from the other 13 known double neutron star systems. In that event, it promises to become one of the best known laboratories for testing theories of gravitation alternative to Einstein's theory of general relativity. Now, since the companion star is also a neutron star, it should also be detectable as a radio pulsar, but that's provided its radio beam also sweeps over the Earth. But sadly, that doesn't seem to be the case for J1913 plus 1102. The authors painstakingly searched all their data for radio pulsations from the companion, but it was all in vain. They simply couldn't find any sign of a radio emission from the companion neutron star. As these neutron stars orbit each other, their orbits shrink because the system is emitting gravitational waves. And the measurements of this effect might allow astronomers to eventually determine the masses of both the pulsar and its companion. Astronomers want to learn more about the little-known stellar evolution of such binary systems. They also want to understand the properties of matter at the density of the atomic nucleus, which is the same as the density of a neutron star. Discoveries like this one are also interesting for the era of gravitational wave astronomy. Finding double neutron star systems like J1913 plus 1102 is useful for the gravitational wave science community. It helps scientists better understand how often these systems merge, and how often advanced LIGO may detect signals from merging neutron star systems in the future. This is SpaceTime. I'm Stuart Gary. If you want more SpaceTime, check out our blog where you'll find all the stuff we couldn't fit in the show, as well as loads of images, news stories, videos, and junk on the web I find interesting, important or amusing. Just go to spacetimewithstuartgary.tumblr.com. That's all one word and in lowercase, and that's Tumblr without the E. You can also follow us through @StuartGary on Twitter. And on Facebook, just go to www.facebook.com/Spacetime with Stuart Gary. Orbital's seventh Cygnus cargo ship has successfully blasted off on an Atlas V rocket carrying fresh supplies for the International Space Station. The Cygnus AO7 spacecraft, named the SS John Glenn, will dock with the orbiting outpost's Harmony module on Saturday. It's the third time Orbital has used the United Launch Alliance's Atlas V rocket for a Cygnus resupply mission. Cygnus is normally launched using Orbital's own Antares rocket, flying from the Wallops Island Flight Facility on the Virginian mid-Atlantic coast. Orbital's decision to use the more powerful Atlas V rather than the Antares for this mission was based on the need to increase the payload capacity for this flight. Two previous flights were switched to Atlas Vs following the launch pad failure and explosion which destroyed an Antares rocket and its Cygnus CRS-3 cargo ship back in October 2014. That failure was eventually traced to the Antares launch vehicle's first-stage AJ-26 rocket engine turbopump. The Aerojet AJ-26 engines are actually former Soviet Union Kuznetsov NK-33 rocket motors, originally built in the 1960s and early 70s. Aerojet purchased 43 of the Russian-made engines in the 1990s, refurbishing 20 of them for use as AJ-26s on the Antares rocket. However, following the 2014 disaster, Orbital upgraded their Antares launch vehicle, replacing the suspect AJ-26 engines with new RD-181 first-stage engines, originally developed in Russia for use on the Energia launcher. The RD-181 provides both greater performance and increased reliability. The Cygnus AO7 spacecraft blasted off aboard its Atlas V rocket under clear blue skies from Space Launch Complex 41 at the Cape Canaveral Air Force Base in Florida.
Status check. Go Centaur. Go OA7.
T-minus 10, 9, 8, 7, 6, 5, 4, 3, 2. Go for main engine start. 1, 0, and liftoff of the Atlas V rocket with Cygnus and the SS John Glenn, extending the research legacy for living and working in space.
Pump speeds and injector pressures look good. HER roll program has begun. Body rates look good. Booster engine continues to look very good. Pump speeds and injector pressures in band. Our D180 continues to perform well, now requesting an mixture ratio change. Booster has begun the zero-angle attack phase of flight. Body rates are right down the middle. Our D180 performance continues to be nominal. Mach 1.
Vehicle now going through the sound barrier.
Max Q. Body rates continue to look very good at this point in flight.
Vehicle hitting maximum dynamic
Booster has
pressure.
throttled back, right on schedule. Signatures look good.
Throttle
Current
back going
altitude
through
is
max
11
Q
miles,
as customary.
5.5 miles. Current velocity is 1,929 miles per hour. Range track shows good progress right down the middle of the corridor. Booster engine performance continues to look very good at this point. The vehicle is now one half of its liftoff weight. Current altitude is 29 miles. Downrange distance 39 miles. Current velocity 4,325 miles per hour. Booster has begun to throttle to maintain 3.5 Gs. Vehicle is now 1/4 of its liftoff weight. RD-180 continues to perform well. Mixture ratio looks good.
The Atlas V rocket used for this mission was in its basic 401 configuration, using a single kerosene and liquid oxygen-fueled twin-chambered RD-180 engine, burning for 4 minutes and 15 seconds before MECO, or main engine cutoff, followed by first stage separation.
And we have BECO. Engine shutdown looks good. We have stage separation.
The Centaur upper stage then ignited its single Aerojet Rocketdyne liquid hydrogen and liquid oxygen-fueled RL-10C1 engine for a 13-minute and 40-second burn to propel the Cygnus spacecraft into orbit.
We have LOX and fuel pre-start. We have ignition and full thrust on the RL-10. Payload fairing jettison has occurred. Looks like a clean step. Centaur steering has been enabled. Body rates look good.
Data now coming in from the New Hampshire tracking station. Still data coming in from the Cape as well.
Engine response looks good. Set MR.
Centaur now steering and powering the rocket.
Centaur is completing the dogleg maneuver. Body rates are now controlling down the middle. And Centaur has begun to roll to optimize telemetry. RL-10 chamber pressures, box pump discharge, and fuel venturi all look good. Centaur currently is flying at an altitude of 191 miles. Downrange distance is 685 miles. Current velocity 10,538 miles per hour. This first burn of Centaur is scheduled for 13 minutes and 42 seconds in duration. All systems continue to look very good.
After placing the Cygnus into a 230-kilometre high transfer orbit, the Centaur upper stage reignited its main engine for a deorbit burn, which brought it back into Earth's atmosphere just south of the Australian mainland. Meanwhile, Cygnus has undertaken a series of manoeuvres to line it up for rendezvous with the International Space Station on Saturday. The space station's currently orbiting at about 400 kilometres. Cygnus is carrying some 3.5 tonnes of supplies, computer equipment and scientific payloads. Also included in the manifest are 38 CubeSats, tiny nanosatellites each about the size of a shoebox. 28 of the CubeSats, including 3 Australian spacecraft, are part of the European Union's QB50 satellite project, a 17-nation international scientific endeavour to launch 50 CubeSats. Each of the QB50 CubeSats carry one of 3 scientific packages designed to undertake long-term in situ observations studying Earth's lower thermosphere. The 3 Australian CubeSats are the first Australian-built spacecraft to be launched from Cape Canaveral in over 15 years. The Australian National University Space Simulator was used to test and qualify all 3 spacecraft for launch and space operations. The ANU also developed power, communications and satellite attitude control systems. One of the project scientists, Professor Christine Charles, who leads the Space Plasma Power and Propulsion Division, says the project's significant because of the growing importance CubeSat technology is playing in the space industry. The 10 by 10 centimetre CubeSats will monitor terrestrial weather between 90 and 400 kilometres above the Earth. Charles says it's a region of the atmosphere that's never been monitored by satellites before. She says the terrestrial atmosphere affected by space weather has a significant impact on satellite communications and GPS systems, both of which are vital to the modern human way of life.
They will be doing multi-point measurements of the upper Earth atmosphere, which contains what's called the lower thermosphere and the ionosphere. They will measure oxygen and nitrogen and NO species, as well as charged electron density measurements in this region of the atmosphere between 90 kilometers altitude and 400 kilometers altitude. So it's a scientific mission at the start.
This is the interaction region where space weather, the geomagnetic storms from the sun, interact with Earth's magnetic field and interact with Earth's terrestrial weather systems.
Exactly. It's really this transition phase and part. And what's really important to see is that there is no strict boundary between the thermosphere and the ionosphere. And this boundary changes all the time on a daily basis, on a seasonal basis, on a yearly basis. So it's very important to monitor this. And it also has a lot of drag, so it influences the trajectories of space debris, which actually is quite important to monitor.
Yeah, when spacecraft are deorbiting, either deliberately or just through normal orbital degradation, they have to take into account the amount of atmospheric drag they're likely to hit at different altitudes. And because the Earth's ionosphere acts like, well, I've heard it described as a giant jelly blubber in space. It pushes in and pushes out depending on how much solar wind is coming from the sun. And so it's constantly changing, and also depending on day and night as well.
Yeah, that's the thing. It's like this jelly, and the models at the moment are very, very rough, so you can't really predict what's going to happen. So we would like to improve the models, and to do this, we're going to have for the first time this multi-point measurement database, if you want, which we'll be acquiring over the next year or so, because we believe that these PD-50 satellites will be able to do all of 160,000 orbits, and we're going to gather all this data, and it's going to be analyzed and put into the models to improve them. So it's at the boundary of terrestrial and space weather, and it's really, really critical. It's not been really investigated thoroughly before.
What does an ion neutral mass spectrometer do?
If you have a molecule or an atom, and if you take electrons, if you rip electron off this atom of molecule, what you end up with is a positively charged ion. So it's a charged particle. So you have negative and positive particles. So let's imagine that you have an O2 or oxygen molecule, two oxygen atoms linked together. You take an electron off and you end up with O2 plus and an electron. So with the ion neutral mass spectrometer, it can run in the ion mode, so you can actually measure the number of these O2 plus molecules, for example. And you can also operate it to just measure the O2 molecules or the NO radicals or the oxygen atoms. So it can function as a neutral spectrometer or as an ion spectrometer, if you want.
It tells you what's up there and how much is up there?
Yes, so if you measure a lot of charged particles, you are mostly in the ionosphere, and if you measure mostly neutral particles, you're lower, you're in the thermosphere. So by seeing what you measure, charge or neutral particles, you can sort of have an idea of where the boundary is and what this boundary is doing and how it is evolving. It's because the Earth is this big 3D system, three-dimensional system, so it's this boundary.
And the other primary scientific instruments include a flax-Phi probe experiment and a multi-needle Langmuir probe.
The multi-needle Langmuir probe is a very nice name. Langmuir was a very famous plasma physicist who did a lot of excellent work in the 1920s. So he invented this Langmuir probe. It's very simple. It's simply a wire, a metallic wire, which you put into your ionosphere or thermosphere. If you put a negative voltage on this wire, it will attract positively charged ions. And if you put a positive voltage on this wire, it will attract electrons. So this is what we are doing. So with the multi-needle Langmuir probe, the multi-needle means that you actually have four wires. You have four probes working at the same time, and you have four different voltages applied to this probe. And these are positive voltages, so you are actually collecting electrons. So with the multi-needle Langmuir probe, you will be able to measure the electron density wherever your satellite is. And with the ion flux probe, which is called FIPEX, it's a measure of the total number of ions which will be around your spacecraft. So a number calibrated per cubic centimeter. So it's just to measure these charged particles.
A lot of satellites as part of this project. This would have to be one of the biggest CubeSat launches in one go so far, wouldn't it?
Yes, in terms of unintegrated international projects for sure. And there are, I think, about 20 countries involved. It's international, it's open source. It's really fantastic to demonstrate to the world that we can have so many countries involving students and professors and engineers and volunteers. It's very important to show that we can all get together and create something really, really good for planet Earth and for monitoring planet Earth. So we are very excited.
And of course, for the ANU, this isn't the only thing we're involved in. You guys have also got a system to test satellites to make sure they can survive the rigors of launch and the trials and tribulations of being in orbit.
That's correct. We have been working on propulsion systems for satellites for the past 20 years. And in the process, we have developed a unique infrastructure in Australia, which has a thermal vacuum chamber or space simulation chamber. It also has what we call vibration shakers. So these simulates the vibrations which the satellite will have to cope with during launch. We also have shock testing facilities, electromagnetic testing facilities. We have a whole range of facilities at the Mount Stromlo Advanced Instrumentation Technology Center in Canberra. So we've been doing this or developing this for the past few years, and it's being used now. So it's really fantastic, and it's top-of-the-line infrastructure.
That's Professor Christine Charles from the Australian National University. The ANU will also use its own ground station to download scientific data and monitor the satellite's operations in orbit. Professor Charles also designed a plasma wind tunnel to calibrate the QB50 miniaturized ion neutral mass spectrometers mounted on 12 of the CubeSats. They'll be used to monitor Earth's thermosphere and study the interaction of space with terrestrial weather. The 3 Australian CubeSats include the University of Sydney's Inspire 2 spacecraft, which is equipped with a Langmuir probe payload, while both the University of Adelaide's SUSAT CubeSat and the University of New South Wales UNSW Eco CubeSat both carry ion-neutral mass spectrometers. As well as the 3 Australian satellites, 9 American CubeSats are also on the mission, including 3 developed by universities and named after the Space Shuttles Columbia, Challenger and Atlantis, which are also carrying ion-neutral mass spectrometer payloads. NASA is also continuing with its own nanosat program as part of this mission, with 2 CubeSats, including the Goddard Space Flight Center's Earth-1 IceCube mission, which is testing a new radiometer to monitor clouds from orbit. Another demonstrator CubeSat on the manifest is the National Reconnaissance Office's Colony 2 program satellite, Biory Point. It's part of a multinational Pathfinder project involving the United States, Australia, Canada and the United Kingdom to develop a constellation of new nanosatellites capable of flying in formation for military applications. Another demonstrator is the Millennium Space Science Systems Altair Pathfinder, which is using a new type of satellite bus design intended for NASA and Defense Department missions. California State University's Northridge Satellite 1 will test new capacitor and lithium-ion power storage technologies capable of operating at far colder, that is minus 50 degrees centigrade temperatures, without needing heating radiators. And Kentucky's Morehead State University's CXBN2 satellite will study cosmic background X-ray radiation. Other spacecraft on this manifest for the QB50 satellite project include 2 South Korean CubeSats named SNUSat-1 and SNUSat-1B. Both carry flux-free probe experiment payloads, while a 3rd South Korean CubeSat, called the Little Intelligent Nanosatellite, is equipped with an ion-neutral mass spectrometer. Taiwan's also included 3 nanosats in the project. The Aozhang-1 CubeSat is carrying the flux-free probe experiment, while its NGES-1 and Phoenix satellites are both equipped with ion-neutral mass spectrometers. And the joint Belgian-Spanish Lilac-Sat-1 CubeSat is also fitted with an ion-neutral mass spectrometer. Finland's first satellite, the Aalto 2, is equipped with a multi-needle Langmuir probe, as are Canada's experimental Albertan-1, South Africa's NSat-1 and Tsar Aerosat, Greece's DuthSat and UPSat, Turkey's Beaglesat, Havelsat and Havelsan, and Israel's Hupi spacecraft. Other CubeSats on the manifest, but which aren't part of the QB50 satellite project, include the French X-Curve Sat and SpaceCube satellites, Ukraine's Polytan 2 Source satellite, Sweden's QB50 LTUOC, and Germany's Student Oxygen Measurement Project or SOMP2 satellite. All 34 of these satellites will be deployed over the next few months from an airlock aboard the space station's Japanese Kaibo Science Module. The remaining 4 CubeSats, which are part of the Lima 2 Weather Satellite project, will be deployed directly from the Cygnus cargo ship following its departure from the space station in about 3 months' time. The Lima 2 weather satellites monitor global maritime tracking identification signals from ships at sea and study GPS navigation signals passing through the atmosphere to determine atmospheric temperature, pressure and humidity. An Indian PSLV rocket, slated for launch next month, will deploy a further 8 of the QB50 satellites. And that's the show for now. You can subscribe and download SpaceTime as a free twice-weekly podcast through iTunes, Stitcher, Bytes.com, Pocket Casts, SoundCloud, YouTube, Audio Boom, your favourite podcast download provider, or direct from spacetimewithstuartgary.com. The show's also broadcast coast to coast across the United States on Science 360 Radio by the National Science Foundation in Washington, D.C., around the world on TuneIn Radio, and as part of Virgin Australia's in-flight entertainment. If you want more space time, check out our blog where you'll find all the stuff we couldn't fit in the show, as well as loads of images, news stories, videos, and junk on the web I find interesting, important or amusing. Just go to spacetimewithstuartgary.tumblr.com. That's all one word and in lowercase, and that's Tumblr without the E. You can also follow us through @StuartGary on Twitter. And on Facebook, just go to www.facebook.com/spacetime with Stuart Gary. SpaceTime is brought to you in collaboration with Australian Sky and Telescope magazine, your window on the universe.
You've been listening to SpaceTime with Stuart Gary. Subscribe at iTunes, Stitcher, Pocket Casts or Audio Boom. This has been another quality podcast production from Bytes.com.